Good afternoon or good evening, everyone. Uh, Welcome to the fourth session of NPTEL. I am Umar Rashid and I am working as a PhD student in Indian Institute of Science, Bangalore. So I am a teaching assistant in this course where every Friday from 6 to 8 I am revising some of the basic concepts in this course, that is Advanced Thermodynamics and Kinetics, and I am also sharing the solutions of some of the problems, and regarding to those problems I am briefly revising the core concepts, the equations, and then using those equations we are trying to solve the problems. Okay, so today is the fourth session of NPTEL. Sorry. Okay, so today we'll have problems and some of the concepts that are related to our previous sessions topics, that is fluid dynamics. So in the fluid dynamics we have diffusion, so we'll be revising some of the diffusion concepts, some of the diffusion equations. Then we have viscosity. Okay, then we have using the kinetic theory of the gases, how we can correlate different parameters like the mean velocity with the both then how we can relate the kinetic theory of the gases to the diffusion. So using these concepts we'll have some problems and we'll try to solve them. Okay, so I will give a brief introduction of what are the topics that we'll be covering today. Okay, so first we'll have some we'll give some introduction. So these are the questions that we'll be trying to solve if the time persists. Okay, and okay, so these are the questions. They are all related to the diffusion and the viscosity, and today I'll first do a brief overview of some of the topics, that is the refinement of mean free path. Okay, so as if we see from the previous session, that is the session third, so these were some of the topics that we have revised briefly from the session third. So I have told heat transfer, what are the different mechanisms of the heat transfer, like conduction, convection, radiation, and vaporization, and how we use heat transfer and how we can see heat transfer into our day-to-day life. Then why we discussed briefly about the heat conduction in solids, heat convention in gases or fluids like liquids, and how it can correlate with the gases law. Then we have seen the observation, like the liquid the currents that are happening in the atmosphere, as well as that are happening while we boil something on a cooking top. And then one of the report from the NASA, where they have seen the convection currents on the surface of the sun. Then we have closely related with the thermal conductivity in case of the solids. So some of the basic concepts of thermal conductivity in solids, where we have defined the thermal conductivity coefficient and the power unit that is transported per unit area, and also the temperature gradient. Then how the thermal conductivity is actually related to the mean speed of the particles and the mean free path, like the electrons in case of the solid is, but we have discussed it with respect to that of an ideal gases. And then we have correlated that in case of the solid, since in case of the metals where we have electrons, so because of the electrons we will have both electron transport, that means the current when we apply the potential, and we have both heat transport. Okay, so that heat transport also occurs majority because of the electrons. So I will briefly tell that as we see the last time, that in case of the gases where majority of the heat transport is happening through the convection, there is actual mass transfer from one part of the gas to that of the another part. And then in case of the liquids, it's also by heat convection. Then I have seen that in case of the solids, right, so in case of the solids, what happens is that the phonons are responsible for the heat conduction, but in case of the metals, we have majority of the heat conduction is happening by the electrons. So in case of the metals, if we take a metal bar, we will have electrons. Now because of that, like according to the electron C model of the metals, what we will have two. If we give a potential across the metal electrode, then what we'll have is these electrons will flow from negative to the positive electron, and as a result we'll get current. Okay, so now that current we will call it as a that current occurs because of the flow of the electrons, because of the temperature gradient. Okay, but the closely related we have is, I think I should report it here. Okay, so briefly what we have is that in case of the metals, we have shown that if we have a metal rod, okay, so and we apply potential across the metal rod, then what we'll have is, this is positive, this is negative, the electrons will flow from this to this. So as a result, we will have electrical conduction, that is denoted by sigma, where R is most probably, sigma is I'll write it rho, this is called as resistivity, L by A. So if we inverse everything, we will have 1 by R, 1 by rho, A by L. Okay, then we correlated, what we'll have is, we'll have a conductance is equivalent to conductivity A by L. So we'll have sigma is equivalent to G L by A. So this is called as a electrical conduction. This electrical conduction occurs because of the application of the applied potential. But in case of the metals also, if what we do is, since the electrons are freely moving in case of the metals according to the electron C model, so what happens is that for example, these are the electrons that are moving, that are quite labile, and then in the meantime we have some positive charges that are actually fixed at their latest positions, right? So then what happens is that once, if we apply a heat on one side, okay, so if we apply heat on one side, then what will happen is that these electrons will move from higher heat, higher temperature, this is T1 here and this is T2 here. If the T1 is higher than this, then what will happen is these electrons will move. The movement of these electrons are correlated, or we correlate it by a factor called as thermal conductivity. Okay, so now in case of metals, as I have shown that electrons are responsible both for electrical conduction as well as thermal conduction, right? So because of these labile or free electrons that are present in case of the metals, this is responsible for exceptionally high thermal conductivity and even also the electrical conduction in case of the metals. Now because of these two, they follow the Wiedemann-Franz law. Okay, so yeah, so this is the Wiedemann-Franz law, where K is called as an thermal conductivity, and sigma is called as an electrical conductivity, and L is called as a Lorentz number. Okay, then in order to to quantify certain parameters, we need the concept of the mean free path. Okay, and how this mean free path is related to that of the mean square velocity. Okay, or we can say mean square displacement. So mean square velocity and mean square displacement is actually, they are actually two different parameters that I will sort of explain in the next. So what we have done is we have used the concept of the mean free path, where we have taken an object, a metal ball for example, whose diameter is d, and we have calculated the effective collision area. That effective collision area is pi d square. Then from that pi d square, we have this is called as effective collision. Then we have calculated the number of the collisions which this gas or a metal ball is going to undergo in particular length, having a velocity t. Now we have correlated it with that of the molecules per unit length. From that concept we have calculated the mean free path. So it becomes 1 by pi d square nv, where n is number density, d is the size of the particle or the diameter, and pi is 3.14. okay, but the problem with this is what we have used here is we have used the nv, also called as a velocity. So as I have written here, the problem with this expression is that here the average velocity of the molecules is used, but the target now we have to see that this is only true when only the molecule for which we are calculating the mean free path is actually moving, while the other particles are static, but that's not actually the case. So other molecules are also moving. So instead of using the nv, instead of using the mean free path, this mean velocity, what we have to use the relative velocity now, and then we have to modify the equation accordingly. So that will be that is our motive for today. Okay, so what we'll do, we'll call it as a refinement of the mean free path. Okay, so yeah, so this is the refinement of the mean free path, where we are taking an average velocity and we are replacing it with the relative velocity, because both the molecules are actually changing. Okay, as I have written here, the in situ development of mean free path expression, this suffers from a significant flaw. It assumes that the target molecules are at rest, when in fact they are also having some average velocity. When needed the average, so instead of using the average velocity, we have to use the average relative velocity. Now if we see that average relative velocity comes out to be under root of average velocity, that we'll see in the next how we can calculate it. Okay, so as of now we can remember that relative velocity becomes under root of average velocity. Okay, so if we use this expression into the effective volume that is swept by a molecule, where it is transversing through a medium. Okay, so instead of a velocity, we'll just change into relative velocity. Okay, so we'll change into relative velocity, then we'll get the effective volume that is swept by the transmitted molecules is pi d square under root of average velocity into t. So we have used just a factor of under root 2 that considers a relative velocity. Therefore the resulting mean free path will become 1 by under root 2 pi d square into n v. So what we had previously is if we are not considering yes, so if we are so this I will kind of close here as of now. So previously if okay, so we are writing the mean free path. Okay, so mean free path is denoted by the lambda. If all other molecules or all other particles are kept at the rest, we will be getting 1 by pi d square nv, where nv tells us the number density, but we use, instead of an nv, we use under root, okay, so nv is doesn't matter. So now what we have to change is, instead of v, which is the average velocity, we have to change it to v average relative velocity, which we have seen, which we'll see that it is equivalent to under root of v relative. So using this equation into this, what will determine what average velocity mean free path will determine is pi d square n v. Okay, so this expression we'll use in question in to solve the questions. Okay. Okay, so now now if we consider this is considered for any material. Okay, now if we consider in case of a gases, we can determine what are the molecules per unit volume, this NV factor, and we can also determine the we can use the that volume from the ideal gas equation. So we know that the number, that is number of the molecules per unit volume, it is given by NV. Okay, N by V. But number of the molecules will also be determined by number of moles multiplied by Na, where Na is called as an Avogadro's number. Now this V, as we are considering the ideal gases, we can use the ideal gas equation, that is PV is equivalent to nRT. So this V will be equivalent to nRT by P. Now we will put this equation, and from this we will determine NAP by RT. So the mean free path for ideal gases or dilute gases, we can say, will be given by RT by under root 2 pi d NP into P. Okay, so this is the mean free path P. Now we have to this equation, as we have seen that we have considered the particles or the gas molecules as hard spheres, but actually the molecules are not sort of an hard spheres, but they are somehow elastic. Some of the energy is actually lost, and also the the calculation of swept distance, like how much the collision diameter, and d is not also this d, that means the diameter of the gas is also changes. So this is not a good approximation. Also in case of the real molecules, they have dipole moment and they have a significant electrical interaction when they approach each other. So for example, if you have one gas molecule and we consider no interaction between them, so there will be no effect of moving of this particle over this particle. But if we are considering the real gases, okay, there will be intermolecular interaction. So what will happen is that the movement of one particle will attract or repel another particle. As a result, there will be intermolecular interaction. So as a result, this expression of the mean free path, it can change. It will depend upon the, so we have to consider those parameters as well in order to arrive the mean free path for real gases. Okay, now what we can do is we can use the concept of the viscosity. Okay, so viscosity is actually the opposition that is given to the flow of the liquid or fluid is called as a viscosity. So it's a way to estimate the mean free path. Okay, so gases have viscosity, fluids have viscosity. Okay, so then if we use those equations, I will not derive here, we can derive that lambda is equivalent to mu, where mu is called as viscosity, P is called as a pressure, pi k T is the absolute temperature divided by 2m. 2m is the molecular mass. Now this equation relates mean free path with that of the temperature and the molecular mass. This equation we will use to derive to solve some problems in the future. Okay, now previously I have shown is that the average relative velocity is under root of relative velocity. Now we have to we'll try to see how it comes. Okay, so for that we'll now, in order to calculate this the mean free path of a gas molecule is necessary to access the average relative velocity of the molecule rather than the average velocity of a given molecule. Now if you see that these are the two gas molecules that we are considering, that two molecules, they are going randomly, like here and here, right, with v1 and v2. Since this velocity is a vector quantity, so the average velocity, so the total velocity between them will be with the vector summation of these two. Okay. Okay, so now if we see that for example, if we consider that now there is a v1 and v2 is sort of moving in the opposite direction, then the relative velocity will be v1 minus v2. So we have to do the vectorial summation. Okay, now if we see that this relative velocity, okay, so it is given by this. Now we know here that relative velocity for these two system, where one gas molecule is going along this direction as v1 and another is going along this direction as v2. Okay, so relative velocity will be this. Now relative velocity is also equivalent to under root of relative velocity dot relative velocity. Now this is a scalar product. Okay, so this expression will take the value of relative velocity from this equation. Okay, it will be this. Then using this equation, using the product, we'll get this derivation. Okay, so the relative velocity here. Now if we see for a scalar product, since this is the dot product. Okay, so dot product of any two vectors is a, if we see that it is a scalar product, it is equivalent to a product of magnitude of 2 as an and cos of theta. If we know that two velocity, this dot product, since v1 and v2 are, they are random. For example, any gas molecule can move in any direction, they are not correlated to each other. As a result, the dot product of this and this, it will be 0. Okay, but we will have v1 dot v2 and v1 dot, this will be v square. Okay, now using this equation and cutting this, what will determine that if both, if for example in a particular gas, if we consider that both v1 is equivalent to v2, we can determine v relative is equal to under root of v, that we have used the equation. Okay, now now we'll move towards the diffusion. Okay, so there are some questions that are related to the diffusion, so we'll try to revise briefly what is the diffusion. Now diffusion, as I have written here, it refers to a process in which the molecules they intermingle as a result because of their kinetic energy of random motion. Okay, for example, if you see two parameters like here and here, we have two containers. Okay, and they have a wall between them. Now this this is a different type of a gas, for example N2, and this is a different type of a gas, for example H2. Now if there is a wall between them, there is no motion. So what will happen is that these gases are at random motion. So what will happen? Nothing will happen. These gases will be confined here, these gases will be confined. If we take this ball apart from each other, these gases molecules, they might move here down the concentration gradient, whereas these gas molecules also go here. So there will be a randomization, so that when they will equilibrate, that means the concentration of this gas molecule over everywhere will be same. This process is called as diffusion. Okay, this diffusion occurs because of the random motion of the gas molecules. Okay, so it will stop, or we will see no net diffusion when the composition of any space in this container is same. So that time we say that it has attained the equilibrium. Okay, now if we see that this diffusion, or as I told you, it comes because of the random motion of the gas molecules. From the kinetic theory of the gases, we can see that mv is 1 by 3 kT sort of. Okay, so the kinetic energy is directly proportional to the temperature. Now if we decrease the temperature, what will happen is that kinetic energy of the gas molecules will decrease. So because of the gas molecules, your random motion will decrease. So as a result, if we give more and more temperature, velocity will increase, kinetic motion will increase, and because of that the randomization will occur more and more. So the diffusion is proportional to the temperature. The higher the temperature, the higher will be the diffusion. Okay, now if we see that diffusion is related to the temperature, so there is since we know that there is the equation. Okay, how diffusion rate is related to the temperature. So the average kinetic energy of different types of the molecules, they are the thermal equilibrium is same, and that their average velocities are different. Their average diffusion rate is expected to depend upon the average velocity, which gives the relative diffusion rate. Now this is the diffusion rate for relative diffusion rate for two gas molecules, and this is diffusion constant, and this directly proportional to temperature and m. Now diffusion rate depends upon temperature and is inversely proportional to the mass of the gas molecules or mass of the molecules that are concerned. Okay, so higher the temperature, higher will be the diffusion, lower the temperature, lower the mass, higher will be the diffusion. So now if we take that we have two gas molecules, okay, now what will be the relative diffusion of these two? So what we will do is we will take this diffusion rate of one molecule, diffusion rate of A, then do K T by M. Now K is actually it depends upon the geometric factors of the cross section. For example, through what is the medium through which they are crossing. Since they are crossing in the same medium, so what we'll see is diffusion rate of A and diffusion rate of B is directly proportional to the square root of their inverse of the ratio of mass of A by mass of B. Okay, so diffusion rate depends upon temperature, diffusion rate depends upon the mass. Okay, now there is the concept of mean square displacement. Okay, so mean square displacement, for example, if we see that we'll take like gas molecules like randomly. Okay, now at any temperature what they will happen, any gas molecule we are concerned, for example this A, it will randomly move, okay, from here to here, here to here, here to here, here to here, here to here. So this is the random motion. Okay, and the average velocity we can determine is determined by the from the Maxwell's distribution at a particular temperature. Now if we take at time t0, for example, the A molecule is at A, is at position X. Now if we take at time t2, after some time, that means the delta t time, it has moved through the random walk to x2. We call the x2 minus x1 as mean square displacement. So this is the, it is the measure of deviation of position of a particle with respect to the reference position over time. How a particle is moving in a medium because of the random walk. Okay, so as I have shown here is that mean square displacement, which is a function of time, we can take as what is the mean of the r from here to here. Okay, total displacement, it is mean. Okay, that we can define as what is the position of the particle at time t and what is the position of a particle at time t plus tau. Okay, so the mean square displacement of any particle in a time period tau will be equivalent to the root mean square of the displacement initially and after the position of a particle initially and position of the particle present over time. Okay, so this is for a particular particle. However, mean square displacement is actually defined with respect to an ensemble. So for an ensemble, what we had to take is you had to take a mean square displacement of all the particles divided by the number of the particles, so we'll get mean square displacement. Okay, so remember it, this is mean square displacement. Okay, so the benefit of using the square is because some particles, if they have a positive and some particles they have a negative, then what will happen is that the total will become 0, but square actually neglects this negative. As a result, we will get some positive factor. Okay, now mean square displacement is also related to the diffusion coefficient. Okay, so mean square displacement using the kinetic theory of the gases, if we use, then it will be equivalent to multiplied by the diameter of the particle. Diffusion coefficient is d, whereas tau is the time period for which it is taken. Okay, now diffusion if we use the kinetic theory of the gases, we will arrive at some equation, that is d naught is equivalent to 1 by 3 v dash into L. So this is by using the kinetic theory of the gases, the equation for mass diffusibility. So mass diffusibility, it tells us that how much mass has been transferred from one place to the another place through diffusion. That is defined by the parameter mass diffusibility, and it is from the kinetic theory of the gas, it is given by 1 by 3, where nu dash is average velocity and L is the distance from initial to the final. Okay, So we have calculated we have given the concept of mean square displacement and how the diffusion coefficient and diffusion flux are related using the kinetic theory of the gases. Cool. Okay, so the another concept that we are going to revise is the laminar flow. Okay, so there are two types of the okay, first I should have done we are going to discuss the concept of viscosity actually. So because of the viscosity we will have laminar flow and we will have this. Okay, so first we'll see the laminar flow. You see, if for example we have a liquid that is passing through a pipe, or okay, so what will happen is that once we press the liquid from here, those liquid molecules that are present here, there will be a resistance to the movement of those liquid particles at the ends, because there will be some resistance that's offered by the wall. Okay, so as a result their viscosity, their movement is very slow. Then next to them their movement will be little higher, then little higher, then little higher, again little lower, little lower, little lower. Okay, so as a result this liquid seems to be flow in different layers of different velocities. Now that flow is called as a laminar flow. Okay, so as I have written here, the resistance to the flow of a liquid is characterized in terms of viscosity of a fluid if the fluid is smooth. In case of moving pellet and liquid, it's found that, so that I have shown here, what is written is that if we have a stationary pellet and we have a fluid inside, and then what we will do is we'll move the upper plate. Okay, so we have two parallel pellets like this. Okay, and what we'll do is we'll move the upper plate. So what will happen is that this upper plate will have will have highest velocity, the liquid that is near to the upper plate. Okay, because this liquid is getting dragged towards the moving pellet, and then we'll have a slow. Okay, so that means this flow is happening in different layers, and this is called as a laminar flow. Okay, this laminar flow, so that means there is actually a gradient of the velocity from here to the here, and this gradient velocity occurs because of the viscosity of the fluid. Okay, and this arrangement of having different layers with different molecular different speeds is called as a laminar flow. Okay, so this is called as a laminar flow, or called as streamline flow. Okay, but what happens is that if there is some object in here, okay, so what will happen is there will be a disturbance in this flow of the liquid. Okay, as a result this liquid will randomize. Okay, then that time this is called as a turbulent flow. Okay, so we can define when a liquid can flow from a laminar flow to the turbulent flow using the Reynolds number, that we'll not going to discuss. Okay, so as I have written here, the common application of the laminar flow would be in the smooth flow of viscous liquids through a pipe or a tube. In that case, the velocity of the flow varies from a zero at the walls to a maximum along the center line. The flow profile of the laminar flow in a tube can be calculated by dividing the flow into thin slender elements and applying the viscous force to them. So technically what we are seeing here is, I will be if we go. Okay, so for example, if we I'm going to cover this. So we are discussing the concept of viscosity. Okay, so I have shown it. For example, if we have a cylinder like pipe, okay, that is here. Okay, then what will happen is that if there is a liquid that is coming from here, like it is like this. Okay, so it is uniform speed. Then once it enters the pipe, what will happen is that there will be this wall will stop the flow of the liquid. Okay, now because of that, what will happen? Okay, now because of that, what will happen is that the slowest liquid will be here. Okay, so this will be the slowest liquid. Okay, so after that, what will happen is that there will be another liquid layer that is moving little faster. Okay, then there will be another liquid layer that is moving little faster than that. okay. Then another liquid that is moving more faster than that. Then there will be another liquid that is moving the fastest, okay, as I have created the gradient. So highest speed will be here, and then the speed decreases. If we take this for example, we see the cross section of this, what we'll see is that we'll see that the topmost layer, this is the slowest, okay. After that it is the little fastest, after that it is fast, okay. And the inner one will be, so they are like sort of a cylinders, okay. If we take a cross section, what will happen is that this is v1, this is v2, this is v3, and this is v4. So v4 will be greater than v3, will be greater than v2, will be greater than v1. This is called as a laminar flow, okay. This we can be characterized based on the viscosity. Now what is the concept of viscosity? This is the resistance that is afford to the flow of the fluid, okay. The fluid include gases as well as the liquids, okay. And similarly, if we take for example a ball and then push inside a liquid, the ball will fall slowly. Now that is also becoming because of the liquid, okay. So this is called as a viscosity of the fluid. Okay, so this is called as a viscosity of the liquid. Now if we say that how we will quantify this viscosity, okay. Now the viscosity is actually considering that the flow of the liquid is laminar, okay. The force that is required to move a plate at constant speed against the resistance of a fluid, which is proportional to the area of the plate and the velocity gradient perpendicular to the plate. The constant of proportionality is called as viscosity. For example, if we take if we see that we are moving a particle, we have a cylinder, and inside this we have a liquid, okay. Inside this we have a liquid. Now if we say that this has one layer, this has multiple layers, okay, and different layers are moving at different velocities, okay. If we consider these two layers, okay, and the difference, that is the opposing force between this and this, the difference in this force is, if for example it is determined by F, that means the higher force that is applied here, because here the higher viscous force will be applied and here little lower viscous force will be applied. So that viscous force, it will be directly proportional to the area of the contact, okay. Then it will be directly proportional to the what is the velocity between them, and how much are they separated from one another, okay. This force is called as a viscous force, okay. So if we take this constant of proportionality, will determine viscosity. So viscosity is defined as force per unit area multiplied by delta y by delta vx, where v is velocity and y is the separation between two liquids, okay. So this is called, this is how to count, this is called as viscosity coefficient, okay. The units of this viscosity coefficient are, as we can see, it is Newton second per meter square, or Pascal second. The CGI units is dyne second per centimeter square. 1 dyne per centimeter, if we say that 1 dyne, dyne second per centimeter square, is actually called as 1 poise, okay. If we see, for example, for in case of the water, the viscosity at 20 degrees Celsius is 0.01 poise, okay. The viscosity of the blood at body temperature, that is 37.6, is 0.03 poise, okay. The also, if we see that Pascal second is called as a Poiseuille, which is equivalent to 10 poise, okay. If we use the kinetic theory of the gases, and we can relate the viscosity coefficient to that of the molecular diameter, that is this, where viscosity is given by n, m is called as wait a second, m is the molecular mass. Okay, sigma is the uh, collision cross section, k is the k, t, pi and m, where k is Boltzmann's constant, t is temperature. So this is like average velocity. Okay, this is from the kinetic theory of the gases. Okay, so if we see that we want to relate the viscosity of ideal gases as a function of the temperature. We know that arithmetic mean, the average speed or arithmetic mean speed is given by 8 by pi kt by m. So arithmetic, so if we see in case of Maxwell's Boltzmann's distribution, okay, so we'll see sort of three speeds. Okay, if this is new, one is coming here, another here and another here. So this is the most probable speed, that is 2 kt by m. Then we have an average speed, that is 8 by pi kt by m. Then we have a root mean square speed. Okay, root mean square, that is 3 kt by m. Okay, so this is the arithmetic mean speed. Okay, so the arithmetic mean speed is kbt divided by pi m. Therefore the viscosity, we can actually, from this equation we can viscosity is given by 1 by 3n 8 kt mt by pi multiplied by lambda. So this lambda is 1 by under root 2 n pi d square. This we have, what we have done is we have used this equation, and from this equation what we have plotted what is the value of lambda. This lambda is mean free path. This mean free path equation we have defined it in this is the mean free path equation that we have defined it in this. Okay, so from the kinetic theory of the gases we can correlate the viscosity to that of a temperature, molecular mass, okay, and also to the to lambda, mean free path. Okay, so so doing some rearrangements, what we can determine is that viscosity is directly proportional to under root of the temperature. That means higher the temperature, lower will be the higher the temperature, higher will be the so higher will be the viscosity coefficient. Okay, so for ideal gases, so higher the temperature, higher will be the viscosity coefficient. Now these equations we'll use to derive to solve some of the questions. Okay, now there are another two concepts, that is the flow, that is how we can determine the flow resistance inside a tube, and also flow speed and Stokes law. Okay, so as I have told before that once a fluid is passed through a through a pipe, so different layers will be offered different resistance. Okay, so we want to calculate that resistance. If we know that flow resistance of a tube is defined as by the relation where this is flow resistance is given by what is the pressure from here. Okay, if this is the pressure here and this is the pressure here, okay, the flow resistance will be this minus this divided by R. Okay, that is the resistance to the flow. Okay, that is the defined as flow resistance. Okay, F is the volume, the amount of the liquid in terms of the volume that is flown through this liquid. Okay, now if we see that F is also the related to the, if the average number of the molecules have effective speed Vf, then we can determine this volume flow by taking this velocity multiplied by the area of the cross section. So what we have done here. Okay, where v effective we have determined as mean square velocity divided by the 2. Okay, and then now we know the how this Vm is related to the pressure. Okay, so we'll put the value of the Vm, that is P1 minus P2 R square divided by L. Vm is actually the maximum flow velocity at the center of the tube. It is here. So the velocity that are given by the particles that is present here will be Vm. Okay, the resistance then this R will be determined by 8 eta L by AR square. Okay, or we can convert this A into pi R square, because if R is the radius of this tube, so we can determine the flow resistance 8NL divided by pi R square. If we define it in terms of resistance force, what we will do is we'll just put it here. F viscous will be given by P1 minus P2 into A, but the difference between this multiplied by the cross sectional area will be equivalent to F R A. Okay, so this equation actually I will derive. So if for example we see that F is equivalent to P1 P2 by R. Okay, if we multiply, it will be F R is equivalent to P1 P2. We can multiply A, we can multiply A. This equation is taken from here. Okay, so we'll get this equation. That is what this equation is plotted. Okay, now we know F has from here, and we know R is from here. So we can determine the flow resistance in a liquid is 4 pi eta LV, where M is called as the maximum resistance. Now we will determine what is the effective speed. Like for example, this is the maximum speed, this is the slowest speed. Now what is the effective speed of a liquid that is passed through a laminar flow? Okay, so the effective flow rate will be expressed as F multiplied by A is the cross sectional area, into V effective. Now we have to determine this V effective. So in order to determine that, what we'll do is we'll determine this F we have to determine. So we'll average, we'll integrate the whole total. We want to determine the total flow rate. Now since we know the flow rate, so we have to integrate it. Okay, so we integrate the flow rate from 0 R to this R, total flow rate. Okay, now we will get V square by 2A. Okay, therefore the V effective is equivalent to Vm by 2. So the effective speed is actually half of the maximum speed. Okay, so the effective speed that is passed through a gas, total effective will be the maximum speed divided by 2. Okay, now there is another law that is important, that is called as this there is another law that is called as a Stokes law. Now Stokes law is actually it quantifies the drag force that is given to an object when it flows through a fluid. Okay, so just 1 minute. Okay, so so Stokes law. So as I have written here, in 1851 the Stokes he derived an expression also called as a Stokes law for the frictional force, this also called as a drag force, exerted on a spherical object with very small Reynolds number in a viscous fluid. Stokes law is derived by solving the Stokes flow limit for small Reynolds number Navier-Stokes equations. Okay, so if we take a Navier-Stokes equation and we use the small Reynolds number, then we can determine the Stokes law. Now so we'll, in the nutshell, Stokes law, the force of the viscosity or drag force that is defined, that is offered to a particular spherical sphere inside a viscous fluid, is given by 6 pi eta R V. okay, where F is the frictional force, also called as a Stokes draw. That is how much when if we have a container like this, okay. So 1 minute, okay. So we'll write, okay. So for example, if we have a container that is filled with some liquid, okay, then what we'll do is we'll take some ball or a sphere, and then we'll put it over this. Now what will happen is that if you will take the same ball in open air and you will put it, okay. Now if this ball reaches here, okay, and the total time taken for this ball is, this is t1, okay, and this ball reaches here and the total time taken for this ball is t2, we'll always see that t1 is greater than t2 with the same distance, okay. That means the ball doesn't fall very fast as compared to that in the air in a viscous fluid. So this, because what will happen is that this ball, once it is put in a liquid, okay, it faces a upward drag force. This is called as a viscous drag. This drag force does not allow it to pass to fall as fast as compared to that in the free air or vacuum, okay. So this is called as a FDR, Stokes drag. This is called as a viscosity. R is the radius of the ball. Obviously the backward force that is offered to a spherical object will be directly proportional to the size of an object, and V is called as the velocity of the ball compared to that of the liquid, okay. So this is called as this is Stokes law. This we will also use, okay. Now if you see that in different diffusive phenomena, okay, so you can have diffusion of momentum, you have diffusion of energy, and you have diffusion of mass, okay. They all are almost similar equations. So if we see here, if there is a momentum transfer, okay, and for that momentum what we will take is, the phenomena is called as a viscosity, okay. The equation is, viscosity is given by minus V dV divided by dx, okay. So there is a change, this is a velocity gradient, right. Similar to this equation, if there is a energy flow, okay, and we define it by Fourier's first law. So this is total amount of the heat per unit area is equivalent to minus K is called as an electrical conduction, is called as electrical thermal conductivity dt by d. This is temperature gradient. And the third is, if we have a mass transfer, okay, it is given by the Fick's laws of the diffusion, and here we have a concentration gradient. So what we had seen here is, diffusion of any kind will happen, okay, when there is some gradient, okay, and the diffusion will happen down the concentration gradient, so from higher to that of the lower gradient, okay. Now that's the reason there is a negative. And then if there is the gradient of velocity, okay, so as a result there will be a momentum transfer, okay, and this physical phenomenon is called as a viscosity. If we will create a temperature gradient, there will be an energy transfer, and this phenomenon is called as heat conduction. If we have a concentration gradient like here, then the molecules will get transferred, there will be mass transfer, and this is called as a molecular diffusion. So if we see, the equations for all of these are similar. We have a constant of proportionality, we have a gradient, and we have the quantity, okay. So using this we have completed the basics of the. Now what we'll do is, we will try to solve the questions, okay. Okay, so these questions are related to the topics and which I have briefly described, and the equations I have shown. So using those equations we will solve those questions. Okay, now the first question is regarding the thermal conductivity of carbon dioxide. So molecular diameter is given and the thermal conductivity is given along with pressure and the temperature. Now we need to find a relation between thermal conductivity and molecular diameter, that I have already shown. Okay, so yes, now what we'll do is we'll take we have a question one. Okay, so what we have is we have to determine the thermal conductivity. Okay, we have shown that that thermal conductivity is given by this equation. Okay, where V knew this V is average velocity. Okay, so this I have shown in my previous lecture, where from this equation comes V is average velocity. We know that from the kinetic theory of the gases, V average velocity is given by okay, CV is the thermal conductivity, CV is the heat capacity at constant volume. Okay, so now what we know, so we have to determine the thermal conductivity. Okay, so what we'll write is that we know that mass of 1 mole of oxygen will be equivalent to molecular mass, that is or molar mass, sorry, 32 grams. Okay, that means mass of Avogadro's number, Na, or in other words 6.023 into 10 to the power 23 molecules of oxygen will be 32 grams, right? Then how much will be the mass of one molecule of oxygen? It will be molar mass 32 gram divided by Avogadro's number. Cool. So we can write it as 32 multiplied by 10 to the power minus 3. We'll put everything in the SI system. Okay, 6.023 multiplied by 10 to the power 23. Okay, so this is mass of one molecule of oxygen. Okay, now that means this is given by m, this parameter. Cool. So we have determined m. Now average velocity will be given by, we'll take 8 multiplied by kb. So I will write here again okay, this is the equation which we have. Okay, 8 multiplied by value of universal gas constant 1.38 10 to the power minus 23 joule per Kelvin multiplied by what is the temperature that is given, 425 K is given. Okay, divided by pi multiplied by, we have m is this 32 into 10 to the power minus 3 kg divided by 6.023 into 10 to the power 23. This whole thing is in under root. Cool. So we will write 8 multiplied by 1.38 into 10 to the power 23 multiplied by 425. This will go here, right? So 6.023 into 10 to the power 23 multiplied by 10 to the power 3 joule divided by this 10 to the power 3 is actually this one. Okay, so it will be 281.25 into 10 to the power 23 minus multiplied by 10 to the power 23 plus multiplied by 10 to the power 3. We have this joule, then we have per kg. This is 1 by 2. This was also 1 by 2. It's in under root. Okay, so using now what we have is 281.25 10 to the power 3. If we see at this one will go. Okay, then we have this joule, we can convert it into Newton meter. 1 joule is 1 Newton meter. Okay, kg inverse 1 by 2. Cool. Then we'll go to the so what we'll do is we'll convert 1 Newton also into Newton is a unit of force. Okay, so it will be kg by per second. Okay, so this I have denoted. If we say that F is equivalent to ma, so F has a unit of Newton, m has a unit of kg, acceleration has a unit of distance, that means meter per second. Okay, so using this equation we have we got here. Okay, so that means my v or average velocity will be equivalent to okay, so average velocity will be 530 meter per second. Okay, now we know that for gases, ideal gases, Cv is equivalent to 5 by 2 R, just like Cp is equivalent to 3 by 2 R, I think so. Yeah, then what we can do is we will write Cp plus Cv is equivalent to R. So what is it? 5 by, or it will be some Cp minus Cv, so I don't properly remember which one is it. So from this we know that for gases Cv is equivalent to 5 by 2 R. Okay, so we know the value of R. We'll write 5 by 2. R is 8.314 joule per Kelvin per mole, that is 20.78 joule per Kelvin per mole. Okay, Now we know the value of CV. Okay, what we'll do is now we'll use this equation. K is given by V we have defined, CV we have defined, then under root 3 by 2 pi d square n a. Okay, so we'll write value of mu average velocity multiplied by value of v that we have determined here, divided by 3 under root 2 multiplied by value of pi multiplied by value of d 420 multiplied by 10 to the power 12 meter, so 420 picometers is given. Okay, then we have multiplied by Avogadro's number. Okay, so K will be given by 11.01 14.15 into 10 to the power calculating this we'll get 7.78 into 10 to the power minus 3 joule per meter per second per Kelvin. Okay, so that is our answer. So what actually we had is we had molecular diameter was given, thermal coefficient was to be determined. Okay, so what we have done is we have used we have used this equation. Okay, that I have shown how to get this equation in the session 3rd of this TA session. So we have first determined the value of average velocity considering it as an ideal gas, then CV considering it as an ideal gas, D is given, Na is given, and we can determine kappa. Okay, so that completes our first question. Okay, now we'll go to question number 2nd. Okay, so the question 2nd is what is the root mean square distance traveled by a molecule having a diffusion coefficient of this in 1 week? Okay, so what we have defined is root mean square distance. The equation for this I have already shown you. Okay, in today's what is the root mean square distance, okay, or root mean square displacement. So what we had to determine, what is the distance traveled by a molecule having a and diffusion coefficient is given. So we had to determine the time in 1 week, and then from the diffusion coefficient we can determine it. Okay, so what we'll do is we'll use the equation that is Z or ms, that means root mean square distance, which is this is given by 2 dt. Okay, so this is our distance, but if we this is Z is 2 dt, but this is in 1 dimensional. But if we have an motion in 3 dimensional, we write r rms whole square then 2 n dt. For 3-dimensional motion, for 3D motion, 3 dimensional 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 motion n is given by 3, so RMS square will be given by 2 multiplied by 3 dt, 6 dt, where d is diffusion. This equation we will use. Okay, so in order to approach the problem, we'll first calculate, we'll say that the square of distance okay, if we have a three-dimensional object, we know that r square will be given by x square plus y square plus z square, right? So if we have a three-dimensional motion like okay, so this is our three-dimensional, this is x-axis, this is y-axis, and this is z-axis, and we'll take some arbitrarily this. Then what will happen is we'll have some x, we'll have some y, and if we see it is impact on z-axis, we'll have some z. So this will be our x, this will be our y, and this will be our z. Okay, so for this we can define this equation. Okay, and this is r, this is x, this is y, and this is z. Okay, for this object. Okay, so this we have defined. Now if we have multiple particles and we want to determine the average, so what we can see is we'll take the average of all. Average of this will be equivalent to root mean square of this plus y root mean square plus z root mean square, not root mean square, mean square. Okay, but if x is equivalent to y is equivalent to z, then what will determine that r square average will be equivalent to 3 z square. Okay, now we had to determine total time duration. That is given by 1 week. Okay, now we had to convert it into seconds. So what we'll do is 1 week consists of 7 days. Okay, multiplied by 1/7 consists of 24 hours per day. Okay, then multiplied by, we have 60 minutes, okay, per hour. Now we have multiplied by 60 seconds per minute. Okay, so from this we'll determine that in a week there are 60.48 into 10 to the power 4 seconds. Okay, as I already showed that ZRMS square is equivalent to 2dt, but for a three-dimensional motion we will write RRMS will be given by 6dt. Okay, so we have diffusion coefficient that is given. So this equation, if you people want to see, it is present in our in my third lecture. Okay, so from the PPT you can get this equation. Okay, so we used D Now what we'll do is R RMS square will be given by 6 multiplied by D. Okay. So what we have taken here is we have taken here displacement. Okay, so that displacement is root mean, this was the square, so we just took the root of this, so we determine the root mean square distance. Okay, so what we have done, the question was we have to calculate the root mean square distance. This is told by a molecule having a diffusion coefficient. We had D and we had T, so we know this equation. Using this equation, what we have seen is we have used this equation, and from that equation we have determined the root mean square and the time in SI units by multiplying, and we have determined the root mean square distance. Okay. Now we have the third question. The third question is related. What is the flux of electrons through a wire of length f if the conductivity of the wire is this and the potential drop across the wire is volt per meter and per V is called as. So we have to determine the flux of electrons through a wire of length L. Okay, and we have been given a resistivity and the potential drop. Okay. So this question is regarding the flux of electrons. So we have another question. Question 3 is regarding the flux of electrons. Okay, so if we know that flux of electrons is if we have a sort of a conductor. Okay, so this is the conductor. Then what we do is there will be electrons inside this conductor, right? So at certain they will move somewhere. Once what we'll do is we'll apply some potential. If this is positive, this is negative, so they will move towards the positive side. This is positive, this is positive, and this I write as negative, so they will move. Now we the flux is like once we apply a potential, what will happen is the electrons will get drifted. Okay, so that we have to determine what is it equal to. Now we know that the variation of, now if the potential delta V is applied, now here it is V1, here it is V2. Okay, so delta V will be equivalent to V2 by V1, that is the potential difference. And if the size the size of a conductor from here to here is L, then we can determine the variation of voltage across the length of conductor. It will be since it will be V by L. Okay, so this is the total voltage fluctuation, like delta V we have defined here as V, and L is the total length. Okay, yeah, but this is also equivalent to delta phi by delta Z, where phi is the voltage. This is the total potential difference that is applied, and phi is the voltage. So change in the voltage as a function of distance is given by minus and now we saw that negative, this negative sign will put here, because negative sign is, as we go on change in the length, negative sign indicates decrease in potential. Across length. Okay, now we have to determine what is the flux of electrons. Okay, so the flux of electrons will be J is given by, okay, minus 1 by conductivity d phi by dz. Okay, where sigma is resistivity and this we have determined from there, right? This we can determine from here. Cool. So we'll write 1 by this, where rho is resist, it is resist, rho is defined in the question as resistivity. 1 by rho is defined as conductivity. So from this we can determine J is given by conductivity V by L. That is our equation. Okay, the flux means the number of electrons that are flowing, okay, per unit time or per unit length. Okay, so number of electrons that are flowing per unit time is the flux. Okay, we can also relate this to the electronic charge or current, and in turn that current can be related to the potential difference. For example, if we relate if we can also correlate it, like we know that current is equivalent to Q by T, right? So current is equivalent to Q by T, but J, which is given by current density, okay, it is equivalent to I by current density, I by A. Okay, so that will be Q by A T. Cool. But we know that current is also given by V is equivalent to IR, called as Ohm's law, right? So that means I will be given by V by R, where V is a potential difference. Okay, since we are potential difference. Okay, now if we consider a one-dimensional conductor, this will be given by Q is equivalent to, here there will not be area, there will be T. Okay, so L by T. Okay, now okay, I is equivalent to V by R, so we'll put here J is equivalent to I will be V by R, for a one dimension it will be L. Okay, so J is equivalent to 1 by R into L. Now if we define everything, now this is in terms of resistance, but if we consider in terms of resistivity, okay, so how is resistance related to resistivity? Resistance is given by resistance L by A, where this is resistivity, okay, L by A. So J is given by V by into A, right? So this A will come here. Now what we can do is, for example, we'll not take it as a J, we'll take it as an I. Oh, I is equivalent to V by L. So okay, so I is equivalent to V by L, V is equivalent to V by R, I is equal to V by R. Now we have to determine the value of R. R is equivalent to this. This is called as resistivity, and R is resistance. Okay, so that means it will give I will be given by V multiplied by A sigma into I. Now I by A will be equivalent to V by L into sigma, but I by A is J, which I have shown here. J, okay, I by A is J, is given by 1 by rho V by L. Now if we say that it is decreasing as a function of length, then we can take a negative value. So that is what we have derived here, sigma V by L, or 1 by A, that will mean J is equivalent to sigma V by L. That is a flux of electrons. Okay, so why we define it electrons? Because since Q is the electrical charge, and J is determined as I by A, so Q will be equal, so this will be flux of electrons. That means electrons per unit area per unit time. Okay, so it is determined by the current. This is also called as current density. Okay, so I J can also be defined as current density. Okay, so we have determined it. Okay, since we have time, we can go to the fourth one. Okay, if the molecular diameter of gas is 350 picometer, what will be the coefficient of viscosity? So we have to determine the coefficient of viscosity at 30 Kelvin, the temperature and the molecular diameter of the gas is given. Okay, so what we will do is, we previously have determined in my I have shown how the viscosity is related to the molecular diameter. Okay, so that we'll use, and using the average speed we can determine what is the viscosity. Okay, so if we look at the first equation here, here, so we have a molecular diameter. This is related to thermal conductivity. So for the viscosity, okay, now we have question third. Question fourth. Okay, the question is regarding the viscosity as a function of molecular diameter. Okay, so molecular diameter, if you see my this PPT, you will see that the diameter or is the relation between the viscosity and the diameter is this multiplied by m divided by 3 under root 2 pi eta whole raised to the power 1 by 2, where okay, so this is the EI, where eta is viscosity coefficient, okay, and V is average velocity. So this is the average velocity, and okay, and the given is diameter is given, it is 350 picometers, that is 350 into 10 to the power minus 12 meters. Okay, so this is given. Now first we know that we have to determine the average velocity. No, average velocity from the kinetic theory of the gases we know is given by 8 by pi kt by m. Okay, so that is taken as 8 multiplied by value of the k okay, then temperature 300 Kelvin. Okay, divided by 3.14 multiplied by mass 20 k. Now since we are considering here molecular mass, not the molar mass, so we have to divide it by Avogadro's number. Okay, Na to Avogadro's number, and also it is, since it is 20 grams, so we have to multiply it by 10 to the power minus 3. Okay, so we will define V or average velocity as 317 what we have converted joules. One, since we know that joule is equivalent to kg meter per second. Okay, so I have used this to okay. So then what we are defined with is coal. Yeah, so we'll get 5.64 564 meter per second. Okay, so we determine the average velocity. Now once we determine the average velocity, we also know that this equation neta is equivalent to average velocity multiplied by molecular mass 3 root 2 multiplied by pi d square, or in other words V m divided by, we have defined this sigma, where sigma is called as collision cross section. Okay, okay, where si- sigma is collision cross section, collision cross section. Okay, so this equation we can find in the PPTs. Okay, so now we know that. So doing a little rearrangement, we'll define d square is given by average velocity m by 3 under root 2 into eta. So now we'll determine d, we have to determine eta, right? Okay, coefficient of viscosity, since we have determined eta, so eta will be equivalent to v, we have determined 564 meter per second multiplied by m is 20 grams, 20 kg, but will then we have 3 under root 2 multiplied by 3.14, this is pi. Okay, 3.14 multiplied by 350 into 10 to the power minus 12 meter square, that means d square multiplied by 6.023 multiplied by 10 to the power 23 multiplied by 10 to the power 3. Okay, so eta will be given by 11.2328 multiplied by 10 to the power 3 meter per second kilogram divided by 9. Doing further calculations, we will reach to this point. Okay, so that will be given by 11.48 multiplied by 10 to the power minus 6 per meter per second kg. Okay, but we know that 1 kg meter per square is equivalent to per second square is equivalent to 1 Newton, and 1 Newton per meter square will be given by 1 pascals. Okay, so what we will do is we'll these two I'll cover. Okay, so we'll use these equations there. What we'll do right is 11.48 multiplied by 10 to the power minus 6 kg, okay, meter per second square multiplied by second divided by meter square. Okay, so that will be given by eta will be given by 11.48 into 10 to the power minus 6 Pascal second. Okay, so our net result is this. So this is our result. So what we have done is we have used this equation that correlates viscosity as a function of molecular diameter and molecular mass. Now you here m, I will write small m, is equivalent to molecular mass. Okay, so we have I have used this molecular mass, that is m, as in the relation between the viscosity and molecular diameter as a relation to determine the viscosity where the molecular diameter was given. First we have calculated the average velocity, then using that average velocity we can okay, then using that average velocity we have calculated the viscosity. Okay, so that completes our question number 4, that is the molecular diameter as a function of viscosity. Okay, now we have another question, that is question number 5, but I don't think we have that much time. So question number 5 is the mean free path and the average velocity, find the value of diffusion coefficient of oxygen and air at them. Okay, so the mean free path we have to is given, and the average velocity is given. We have to find the value of the diffusion coefficient. Okay, so this we'll take in the next session. So we have up to 4 we have done. From 5, 6, 7, 8, 9 and 10 questions will take in the next questions. Okay, so all this material will be available on the Google Drive, as well as this recording will be available on the YouTube. Okay, so thank you so much everyone, and if there is any query or any question, please let me know. Thank you so much.